Milen Yakimov, now from Northeastern University. Well, an integral part of Southeast Lee Theory Network. I hope he continues to be part of it. Yeah, so the title of his talk is Non-Commutative Tensor Triangular Geometry and Support Variety for Hopf Algebras.
Thank you. This is the microphone. Excellent. I keep the mask or I take it out? What? Please, I keep the mask or I... Excuse me? It's a little bit of a break. Okay, I'll keep the mask. I just wanted to know like what's the rule. Perfect. Thank you. Okay, so I just wanted to start by saying a few words about Ben Cox. Like everybody else said, I very much seeing him here among us. He was a wonderful mathematician, and I learned a great deal of math from him. And he was a very kind and humble person, and I have very fond memories of time that we spent together. And today is the second day of the 12th Southeastern Lee Theory Workshop Series, and my fondest memory of Ben Cox is from the first. So the first is the one that was organized by Keller, Stan, and Brian Parshow exactly 12 years ago. It's 12th anniversary. It was October 9th through 11th of 2009. So I want to say happy birthday to Dan Keller and Brian Parshow for this wonderful conference series. And we spent a lot of time with Ben Cox during that meeting. We were going together everywhere. He drove me to the conference dinner. We sat together and we talked about many things that I don't really remember now, but it was a wonderful time. So he's really going to be very much missed among all of us. So the thing that I want to talk today about is a joint work with Dan Nakano, with one of the organizers. I thought it's always good to do work with the organizers to get invited. And with our joint former graduate student, Ken Vesho, who is at MIT now. And in this talk, I want to address a couple of major problems about Hopf algebras. So through the talk, A is going to be a finite dimensional Hopf algebra over a field K, which is algebraically closed. And we're going to denote by little mod A the category of finite dimensional modules over the algebra A. So the first problem is the so-called problem for the tensor product property map for the cohomological support of the Hopf algebra. And it goes as follows. We look at the cohomology ring of the Hopf algebra, which is the sum over n greater or equal than 0 of the X groups of the base field with itself. And this is well known to be graded commutative, all the case, all the time. And for every module M in there, this acts on the X of that module. So this is again the direct sum over n greater or equal than 0 of all X groups of the module with itself. And based on this module, we define the cohomological support of the module M to be the sigma of M, which is the set of all prime ideals in proj R, with the property that this contains the annihilator R of the module that we just created, M. So the question here is, when the cohomological support of the tensor product of two modules is the intersection of the two cohomological supports. This problem has a long history, and I will come back to this history. The second question, the second problem is the following. So we are looking at our category of finite dimensional representations over the Hopf algebra A. So I'm sorry, I felt the urge that I should write on the board. So my talk is because of COVID. So I hate the transparencies and everything. And my talk will be much slower than all the other talks. So sorry about that. So it's going to be very slow. So we look at the category of finite dimensional modules of A. So in this category, all projective modules are injectives because every finite dimensional Hopf algebra is self-injective. So this is a Frobenius category. So we can form the corresponding stable module category, which by definition is taking all objects, same objects. But the home spaces in the stable module category are the home spaces in the original category, factored by all morphisms that factor through a projective module. This category is no longer abelian, it's triangulated. So mod A is triangulated. It inherits the tensor product, which is symmetric. And the ideology now is that the problem of classifying the indecomposable modules over A is wild, but we want to replace that with a problem that's tractable, and that will be question 2. Classify all thick tensor ideals of mod A. And let me just recall quickly that if we have a triangulated category, a thick subcategory C of a triangulated category, like the one that we're looking around, is a triangulated subcategory which is closed under taking direct summons. So the idea now is this looks like sort of very different problem from the original one. The original one was just a problem about cohomological support. This is about ideal structure of a certain symmetric monoidal triangulated category. However, over the time, people have discovered that these two problems were very much related, and I will come back to that. Now, there is a lot of history on this and a lot of major results. So first, I want to look at the case when A is the group algebra of a finite group. So question 1 has a very famous positive answer, yes. That's due to Len Scott and Avrunin. And Scott from 1982, almost 40 years ago. Question number 2 has a cosification due to Benson, Carlson, and Ricard. If I remember correctly, this is about the mid-90s. And once these things were done for finite groups, people moved to the situation when A is co-commutative. Saying that A is a co-commutative Hopf algebra, which is finite dimensional, is the same thing as saying that you look at the representations of finite group schemes and the two positive answers of question 1 and question 2 were extended to that situation by Friedlander and Pertsova. And this was in the early 2000s. towards the middle of the early 2000s, maybe towards the end of the early 2000s, came a very influential work on tensor triangular geometry by Ballmer, who discovered that there is a common player in the game, and this common player in the game is the spectrum of the stable module category of A. So here A is still co-commutative. So this is going to be a symmetric tensor triangulated category. And the spectrum of this triangulated category is the set of all two-sided ideals of mod A. So by less or equal, I will denote the set of thick, not two-sided, the set of thick ideals of this symmetric monoidal triangulated category, which are prime in the sense that M tensor N belongs to P, implies that either M is in P or N is in P. So at first it did look like we're trying to generalize the risky spectrum in a very direct way, but then eventually turned out that no, that's not the case. This was actually a very common player between the two questions, 1 and 2. And what I want to somehow say today is a story about a non-commutative version of this and how we can use the non-commutative version to approach those two problems in general for general non-commutative, non-co-commutative finite dimensional Hopf algebras. And the whole story is still very open. This is an extremely difficult problem. For instance, it's still unknown whether that cohomology ring, which is graded commutative, is finitely generated, whether it's Noetherian. So a lot of things are out there, and this is a difficult problem. So there is no expectation that this can be resolved within a year or so. So here's our contribution to this story. So now we are looking at mod A. So this is the stable module category of finite dimensional representations of our non-co-commutative Hopf algebra. And this is a special example of a monoidal triangulated category. So what is this kind of gadget? So first we have a triangulated category K with certain triangulated structure. It has a tensor product, which is biexact. So the whole point in some way to moving to the triangulated setting is that tensor products that are not exact on the abelian level eventually will become exact on the triangulated level. So having this biexactness is something that we have around all the time, and we have an identity object 1. So in a simplistic way, we can think that this is just a triangulated categorical version of a non-commutative unital ring. And now we want to do a certain kind of geometry with this non-commutative unital ring and start with exactly the same idea that people had in non-commutative ring theory. So we say a definition, a thick ideal P of a monoidal triangulated category. This will be the abbreviation for monoidal triangulated category. We wanted to use MTC, but that is already taken.
Can you write a little larger or use a thick stroke?
I think this is the thickest.
Okay.
Thank you, Wei Chiang, but I think, unfortunately, this is the thickest for some reason. This is the 97 size, and the other one is 50. So I will try to write bigger letters. So I take idea of a monoidal triangulated category K is called prime if for every two thick ideals Ij, I tensor J sits inside P, implies that either I is inside P or J is inside P. So for those of you who have seen the spectrum of a non-commutative ring, we're doing nothing here, we're just imitating that. And equivalently, this condition can be phrased in the following way. If I have an object M and N such that this belongs to P for every object Q in our category K, then this would imply that M is in P or N is in P. So the story is that in the non-commutative situation, we have to stick there an arbitrary object. And that's somehow like the correct definition of a prime ideal. There is a definition of a completely prime ideal. And completely prime ideal is a property that M tensor N is in P, implies that M is in P or N is in P. And we have an implication this way, but we don't have an implication in the opposite direction. So we're doing everything on the categorical level, but it's somehow a good idea to keep in mind all the time what really happened in non-commutative ring theory. And in non-commutative ring theory, we have a famous theorem of Dixmier that said that if you look at the universal enveloping algebra of a finite dimensional Lie algebra, then every prime ideal is completely prime if and only if G is solvable. So that is somehow like a good example for why we shouldn't really stick to these completely prime ideals. And I'm going to come back to this. People did try to do this in this setting, and somehow they failed for several algebras, and those will be examples of how the methods that we wanted to develop work for those Hopf algebras. But here is this theorem of Dixmier that basically tells us that on the level of rings, not triangulated categories, this is the right thing to do. All right, so now we define the SPC of K, which is a monoidal triangulated category, to be the set of all prime ideals with a topology in which the closed subsets, the family of closed subsets is generated by the following sets in the following form. So M is an object in K. This is the set of all prime ideals in SPC K, such that M is not in that prime ideal. And when you see this at first, it's kind of striking because when you define the Zariski topology, you want inclusion, not exclusion. But for some reason that somehow takes longer to explain, this is the right thing to do here. And this does define a topology. And this is the generating set for the set of closed subsets. So this is our topological space that's going to be the main player around. And on the basis of this topological space, we will try to develop certain methods to classify the thick ideals, all thick ideals, not just the prime ones, and also to treat the tensor product property for the cohomological support. Now let's try to axiomatize what is a support datum. So support datum. Now we want to axiomatize this on the basis of this idea. So first, this is going to be a map that takes objects, like it's common, I'm going to denote in the same, with the same symbol, the set of objects of our triangulated category, to the closed subsets of a topological space X. So this is a topological space, and this is the family of closed subsets. So support datum is going to be a map of this form that's going to have some properties. These are the very standard properties. They have been around, most of them, so nothing really rocket science here. Sigma of the zero object should be always empty. Sigma of the identity object should be the whole topological space. Sigma of a direct sum of two modules, objects, should be the support of the first union the support of the second. And once again, I want to emphasize these are properties that have been around since the 70s. So these are expected properties of support maps. So 3, the support map should be invariant under the shift functor of the triangulated category. 4, if I have a triangle M goes to N goes to Q goes to sigma M, then this implies that the support of M is inside the support of N union the support of Q. Still nothing. So finally, I have to use the tensor product. We have never used the tensor product here. So in order to use the tensor product, now the driving force is we think about support datum for objects, like support datum for modules. This is what we really want to work with. However, we're going to formulate everything in terms of ideals, because the ideals are the things that we can capture, not the individual objects. And in order to capture everything on ideals, we extend sigma to a map that will be called phi sigma from the thick ideals of K to the specialization closed subsets of X. So before we were working with the closed subsets. Now we're going to work with the specialization closed. And specialization closed subset is just arbitrary union of closed subsets. We define that F sigma, this is the extension of an ideal I, to be just the union over all objects in this ideal of the supports of those objects. Remember that those supports are going to be closed subsets. So when you take the infinite union, there's no way you will get a closed subset in general. That's why we have to work with the specialization closed subset. And now the definition, the fifth part of the definition is that the phi sigma of I tensor J has to be equal to the phi sigma of I intersection with phi sigma of J. So this is now our axiomatization of water support data that would go with an arbitrary monoidal triangulated category that does not have to be symmetric in general. So here is an example. If I look at the spectrum of our category, then I'm going to have a universal support datum. It's the map V that takes K to the closed subsets of the spectrum. And V of an object M is precisely what we defined. This is the closed subset of those P in the SPC that miss M. So we have our universal support datum, but if we have a triangulated category that comes from a finite dimensional Hopf algebra, it will also have the cohomological support datum. So somehow we will on one side try to address the thick ideals by looking at the spectrum, and on the other side we will try to capture the properties of the cohomological support by looking at this universal support. And in order to be able to prove anything about such arbitrary support data, we have to have some theorems about this universal support data. That's the next thing that I want to tell you. And the first will be universality theorem. And this is with Dan, Ken. Bless you. And the theorem says the following. V from K to SPC K, specialization closed subsets there. Let me erase this to make it nicer. For some reason, when you tap this twice, it should move from one to the other, but for some reason, I can't make this feature work. So this one is the terminal object in the category of all support data for K. So what does this mean? So that means that if we have any other support datum sigma from K to closed subsets of any topological space, then there exists a unique continuous map F that goes from that topological space to SPCK. So that time that direction should remind us that this is a universal terminal object, such that the following diagram commutes. So I'm going to start with the thick ideals of K. First, I have that extension phi sigma of the support map sigma. This is to the specialization closed subsets of X. Then I have the extension map for that universal one that comes from the spectrum, SPC of K. And if I have a continuous map, I can do pre-images. So this is F sigma inverse. And the statement is that for this map F sigma, we are going to have a commutative diagram like this. This is the universality property that uniquely determines F sigma. So this is how we get that this support datum that comes from the spectrum of the category is universal. Now, on the other hand, of course, this is a nice abstract notion, but if we can't compute it, then who cares? We can't do anything with it. So we need to have reconstruction theorems. So here is one of the reconstruction theorems that we have. Reconstruction theorem. And again, that's with Dan, Kent Wessel, and myself. And it says the following. So now we want to construct a support datum of a particular form and use that support datum together with the universality to reconstruct our universal one. So that's the ideology. And here is how it works. Assume that sigma from K to the closed subsets of X is a support datum that has the following properties. So one, it has an extension. I'm going to call that extension sigma hat from another category that will be much bigger K hat to all subsets of X, where that K hat is a monoidal triangulated category that is big. This is going to imitate the big category of modules over Hopf algebra that has arbitrary set indexed coproducts. And our original one is the compact part of this category. So think in terms of infinite dimensional modules versus finite dimensional modules. In infinite dimensional modules, in that stable module category, we have arbitrary set index coproducts. The finite dimensional modules are precisely the compact part of that one. A couple of technical conditions that I somehow want to throw under the rack. Sigma hat should be faithful. In particular, that means that if the image of some infinite dimensional object there is empty, then this would imply that that object is the zero object. And this is the two-sided ideal that's generated by M. Two-sided ideal generated by M. Two-sided thick ideal. So it's a thick subcategory that's generated by M. And a realization property for every W that is a closed subset of that topological space, there would exist an object M in the compact part such that the image of the corresponding ideal is going to be that closed subset. Then here are the implications out of this. The first implication is that topological space X actually has to be isomorphic to SPC, homeomorphic to SPC. So in other words, we managed to completely recover the SPC from that X. And two, there exists a bijection between thick ideals, thick two-sided ideals of K and the specialization closed subsets of X. So somehow with one-shooting, we managed to solve two issues at once. The first is to reconstruct the topological space, and the second to classify the thick ideals, not necessarily prime, all thick ideals of the category. And again, the ideology in this area is that looking at the classification problem for indecomposable modules is a wild problem. So whatever you do, you won't be able to classify those. But you should at classifying the thick ideals, which is something that's tractable. So this is of something how that could actually work. So let me mention a couple of examples that are applications of these theorems. So the major counterexample in the area that somehow all the previous approaches failed is an example of a Hopf algebra that's called the Benson-Witherspoon Hopf algebra. So Benson-Witherspoon. So this is a Hopf algebra for which the previous approach is to build some sort of non-commutative tensor triangular geometry failed. And here's what we do. We look at two finite groups L and G. So these are two finite groups. And the group L acts on G by automorphisms. And we assume that we have a base field whose characteristic K divides the order of the group G on which we act. So this is our modular situation. The Hopf algebra that we're looking at is the group algebra of the algebra of G, the group algebra of G. I'm going to dualize it. I'm going to take the smash product with the group algebra of L, and then I want to dualize it one more time. So now this is a very nice formula, but I want to tell you what this formula really means in concrete terms. So in concrete terms, this means that A modules are the same thing as L graded G modules. So it's all very good, like it's really something very concrete, something that you can use usual support theory, like the one for which Lamb proved the tensor product property 40 years ago. But at the same time, our tensor product is twisted because of this smash product there, the tensor product gets twisted. So the theorem for this one is again a theorem with Dan Kent. Says that one, the SPC of mod A is precisely the proj, so it's homeomorphic to the proj of the cohomology ring of the group G, fixed points under the L action. So here we sort of managed to completely classify our topological space. And two, this is the punchline. If I look at two-sided thick ideals of mod A, these are in bijection with the specialization clause subsets there. Specialization clause subsets of proj H dot G L. So in other words, our topological space actually sees those two-sided ideals in the sense that the two-sided ideals became precisely the set of specialization clause subsets of that space. And at the moment, there's no way to basically, for any Hopf algebra or monoidal triangulated category, to go straight. We need to prove some theorems that are not easy at all in order to relate thick ideals to specialization clause subsets of some space, and then prove that that subspace is precisely the spectrum that we started with. So we wish there is a direct way to go that way, but that at the moment is too much to hope for. Here is a second theorem. Where we'll look at the small quantum Borels of all small Lustig quantum groups. So these are going to be U, zeta, B. So these are the small quantum Borels in the small quantum group of arbitrary finite type G. Zeta is a root of unity of order L. And we will have some standard assumptions on this. I think we have the assumption that L is odd, but I might be wrong about this. We have the assumption that L is bigger than the Coxeter number. And we have the assumption that the GCD of L and a finite group, this is a finite group that you've seen in many different ways written, but I'm going to write it here just quickly for the quickest way of writing it down. Weight lattice modulo root lattice is equal to 1. So use whichever model you like for that finite group. There are several ways of saying what is that order. So if that condition holds, then the SPC of mod U zeta B is homeomorphic to the proj of S dot N, where N is the new radical of B. Due to work of Ginsburg-Kumar that was much expanded later by Bendel, Nakano, Parshall, and Pilon, this is precisely the homology ring of the small quantum Borel. So we have that the SPC is that, and 1, and there is a bijection, two-sided, thick ideals of mod small quantum Borel. Let me throw parentheses here. This is in bijection with the specialization clause subsets of proj S dot N. And again, so in this theorem, once again, we get that if we look at all two-sided ideals, those are the specialization clause subsets of some topological space, which is precisely the spectrum of our category, this non-commutative spectrum. And there is no way to simply move directly between those two objects. It will be extremely desirable to have a direct link between our non-commutative space and the set of all thick ideals. But that's again way too much to hope for something that in general, like there is quite limited knowledge at the moment. In the last, so I started at 10:40, so 10 more minutes, 11 minutes. Super. I should fight for every minute. writing down on the board is exciting because it's sort of post-COVID type experience, but at the same time is slow. So it is what it is. So at the last, for this last portion of the talk, I want to somehow try to persuade you that this non-commutative thing was the right thing to do. That's goal number one, as opposed to just straightforward generalization of Ballmer's work. And secondly, how we can treat the tensor product property. All right. So start with our universal support. This was a map from the object of our category K to the, let me erase, to the specialization closed subsets. Specialization closed sets of the spectrum. And there are many other support maps. So we were thinking about approaching that problem when a support datum map has the tensor product property. So the tensor product property is that the sigma of tensor product of two objects will be sigma of m intersection sigma of n. Just like I said, this is a fundamental property in the case of finite groups. It's due to Len Scott and Avrunin. And there's been a lot of effort to basically understand in what generality you have support maps that satisfy this property. And this is not simply a game that you want to say like, I really want this nice property. It looks nice, but it's not just it looks nice, it has consequences. And the point is, if you prove that it has that property, then you can use the consequences. So our way of thinking is, we really want to approach this problem in general for the cohomological support for a Hopf algebra. But that so far is out of the picture, like using the universality, we're going to connect that to the universal support datum. But the really fundamental question to start with is when the universal support datum will have that property. So this theorem is answering that question. So the universal support datum map V, it's that one, has the tensor product property. If and only if every prime ideal of K is completely prime. And this, like I said, is a major property that people cared a lot in ring theory, but not on the triangulated level. It was on the level of non-commutative algebras. So just like I mentioned, Dixmier proved that for every finite dimensional Lie algebra G, U of G has that property if and only if every prime, if and only if G is solvable. So if you wish, the problem now becomes, we want really to classify Hopf algebras for which their stable module categories have exactly that Dixmier property. So in other words, they're solvable in some way. So if this is eventually achieved, then this will be really a big understanding in terms of like what are those Hopf algebras that will have that property. But for the moment, we don't really have a definition of when a monoidal triangulated category is solvable. So there's not even a candidate for that notion. But eventually, that will be somehow one way to look very generally at the tensor product property. It's a solvability on the triangulated level. And that solvability has nothing to do with the Hopf algebra. So it's one thing is the Hopf algebra, but the other thing is its representations. in saying what it means for its representation category to be solvable, somehow completely different property from any property of the Hopf algebra. So this is our theorem. And now based on this theorem, we can prove, we can have consequences of the theorem. And here is one consequence. So this is a theorem again by Dan, Kent, and myself. And this is a conjecture by Negron and Pevtsova. And this conjecture says that if L has the above properties, the restrictions on the root of unity, then the cohomological support for the small quantum Borel U zeta of B has the tensor product property. So that tells us that we have, hey, we have another Hopf algebra for which we can prove the tensor product property. But on a more deep level, this comes from the fact that if you look at the module category of U zeta B, it has a very remarkable property. On the one side, the tensor product is non-commutative. So this is like a non-commutative ring. But on the other side, it has the property that every right ideal, right thick ideal is two-sided. So combining the theorem that we had before, that theorem, and this property that actually can be deduced from the previous theorem that we proved about the classification of thick ideals, combining those two is actually leading to the proof of that conjecture. And if you think about it, it's a very interesting property. Like, think like if you are not in the categorical level, but you were on the level of rings, think if you have an example of a non-commutative ring that has the property that every right ideal is also two-sided ideal. It's not easy to come up with such an example, but it's a sort of interesting thing to think about. This is how the small quantum Borels look like. They have that very interesting property. And finally, I want to finish with the Benson-Witherspoon. So like I said, it sort of failed all previous approaches to non-commutative tensor triangular geometry. And the theorem here is that the Benson-Witherspoon, again, this is a theorem with Dan, Kent, theorem with Dan, Kent, says that the Benson-Witherspoon Hopf algebras in general do not have the tensor product property. And let me just say very quickly where the examples come from. So the examples come from things like this. So I have a group L that acts on a group G. So we take that group G to be Z mod P raised to power N. And we take L to be the Z mod N that acts on that in a cyclic permutation way. And the other examples are coming from G being the Klein 4 group, Z2 times Z2, which is identity E1, identity A1, A2, A3. And we take L to be Z3, that again permutes those three generators of the Klein 4 group. And where everything comes, so this is how the groups look like on the category, but where everything comes, why everything here, what is causing the tensor product property to break? What really is causing this tensor product property to break is the availability of two conditions that happen simultaneously. First, every object M in K is dualizable. So it has a dual M with some property. And second is something that you like or you don't like in algebraic geometry. There exists a non-zero object M in K that is nilpotent. And those objects, the objects of this kind, were constructed by Benson Witherspoon. So our contribution here is to say that this actually implies that there exist prime ideals that are not completely prime. And now that by the other theorem causes failure of the tensor product property. So in a sense, this is my final justification. Why do we really need this non-commutative tensor triangular geometry? If we were simply trying to copy Balmer, then we would be simply working with these completely prime ideals. Those completely prime ideals are going to form a topological space that is going to be strictly contained in the spectrum of this. So it will be strictly contained in that spectrum of the category. And that topological space would simply not be enough to capture all ideals, to capture the tensor product property. And we will need that bigger space. So these are examples where that bigger space is really bigger, and simply we cannot work with the smaller. So that's all that I wanted to say. And thank you again.